Everything we know about the universe leads us to a single moment. About 13.8 billion years ago, the universe was born, but this birth was not an explosion in the way we usually imagine it. There was no center. There was no empty space expanding outward. The Big Bang was not an event that happened in space. It was the moment space itself began to expand. Time emerged at that very moment. When the universe came into existence, it was not only matter that appeared. Time itself was born as well. Here, we encounter a fundamental problem. The human mind understands reality through before and after. But what does before mean when time does not exist? If time began with the Big Bang, does it even make sense to talk about something before it? This question challenges not only cosmology, but the way we think about reality itself. Because without time, there is no change. And without change, there are no events. That is why scientists today state something very clearly. The Big Bang was not an explosion that occurred within the universe. It was the beginning of the universe itself. So what existed before this beginning? Was there truly nothing? Or was there a reality we do not yet understand? The answers to these questions do more than explain the origin of the universe. They help us understand the nature of reality. If questions like these make you curious, and if you want to explore the universe through science, you can become part of this journey by subscribing to the channel. Now we go deeper, because in the next section, we will examine what we really mean by nothing and whether there was truly nothing before the Big Bang. The Big Bang Theory is our most successful scientific model for explaining the origin and evolution of the universe. It does not describe how something exploded into empty space. Instead, it explains how space, time, matter, and energy emerged together from an extremely hot and dense state. According to this model, the early universe was compressed into conditions far beyond anything we can recreate today. There was no outside and no surrounding void. Every point in the universe was once closer to every other point than we can meaningfully imagine. As time passed, the universe began to expand, not by moving outward into something else, but by space itself stretching. This expansion is not a theoretical assumption. We observe it directly. When astronomers look at distant galaxies, they see that almost all of them are moving away from us. The farther a galaxy is, the faster it recedes. This tells us that the universe is not static. It has been expanding for billions of years. Another crucial piece of evidence comes from a faint glow that fills the entire universe, the cosmic microwave background radiation. This radiation is the afterglow of the early universe, released about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely for the first time. Today, it is detected as microwave radiation, coming uniformly from every direction in space. Its existence, temperature, and structure match the predictions of the Big Bang Theory with remarkable precision. It is one of the strongest confirmations we have that the universe began in a hot, dense state. But what about the very beginning? When we trace the expansion backward using physics, we arrive at a limit known as the Planck time. This is the earliest moment our current theories can describe. Approximately 10 to the power of minus 43 seconds after the beginning. Before this point, gravity, space, and time behave in ways we cannot yet fully explain. Our equations stop working, not because the universe ends there, but because our understanding does. This is why the question, what happened before the Big Bang, is so difficult. The word before assumes time already exists, but if time itself emerged with the Big Bang, then asking what came before, it may be like asking what is north of the North Pole. The question might not be unanswered. It might be ill-defined. Still, scientists continue to explore possibilities, from quantum models of the early universe to ideas involving cyclical universes or deeper structures of reality. The Big Bang Theory does not claim to explain everything. What it does offer is a clear, testable framework for how the universe evolved from its earliest measurable moments to the vast cosmic structure we observe today. And it brings us back to the core mystery. If the universe had a beginning, what does that say about the nature of existence itself? We often think of time as something independent from the universe, as if everything happens within it. Modern physics, however, presents a very different picture. One of the key figures who shaped this view is Albert Einstein. Einstein's general theory of relativity does not treat time and space as two separate concepts, but as a single structure, space-time. The shape of this structure is determined by matter and energy in the universe. Time is not a clock standing outside the stage. It is part of the universe itself. This perspective fundamentally changes how we understand the Big Bang. If space-time is a result of the universe's structure, then time must have emerged together with the universe. In other words, time is not a background that existed before the universe, but a phenomenon born with it. When the equations of general relativity are run backward, we reach a point where the density and temperature of the universe approach infinity. This point represents a boundary where space and time begin to lose their meaning. Here, concepts like before and after no longer apply, because these concepts require time to exist. Where there is no time, cause and effect cannot be defined. Yet this is precisely where we reach the limits of science. General relativity is extremely successful on large scales. It explains the motion of planets, the behavior of stars, and the expansion of the universe with remarkable accuracy. But on very small scales, especially in the earliest moments of the universe, it becomes insufficient, because in this regime, quantum effects become dominant. And today, we do not yet have a theory that fully unites quantum mechanics and general relativity. This means that at the very beginning of the Big Bang, we cannot say with certainty how time truly emerged. Science does not stop here, but it proceeds with caution. Because once we go beyond mathematical models, speculation begins. Some theories suggest that time may be the result of a deeper underlying structure. Others argue that time is not a fundamental concept, but an emergent property. One thing is certain, time is not as simple as we think. And as we try to understand the beginning of the universe, we are not only questioning cosmology, but the most fundamental nature of reality. For this reason, the question, did time begin with the Big Bang, is not only a question of physics. It marks the boundary of human knowledge itself. As we move closer to the beginning of the universe, clarity does not increase, it fades. The earliest boundary science can reach has a name, the Planck wall. This wall corresponds to a moment approximately 10⁻43 seconds after the beginning. This interval is known as the Planck time. It is the smallest unit of time we can calculate or meaningfully describe. Before the Planck time, the laws of physics as we know them break down. Space and time no longer exist in their familiar forms. The universe becomes unimaginably dense and unimaginably hot. So why can we not calculate what came before this point? Because here, the two foundational pillars of modern physics collide. On one side is general relativity, the theory that works on large scales, explaining planets, stars, and the expansion of the universe. On the other side is quantum mechanics, the framework that governs the subatomic world, ruled by uncertainty and probability. Both theories are extraordinarily successful within their own domains, but at the Planck scale, they cannot both be applied at the same time. General relativity treats space-time as smooth and continuous. Quantum physics tells us that reality is discrete and uncertain. At the Planck time, these two perspectives clash, and as a result, the equations collapse. This is why the Planck wall exists, not because it marks the true beginning of the universe, but because it marks the limit of our knowledge. Science does not fall silent here. It admits that it cannot yet move forward. What lies beyond this point belongs to a physics not yet discovered. Theories such as quantum gravity attempt to fill this gap, but as of today, no model has been experimentally confirmed. This is what makes the Planck wall unique. It is not a locked door in the universe, but a door we have not yet learned how to open. And perhaps the most important question is this: is there truly a before beyond this wall, or does time itself completely lose its meaning there? For now, science cannot answer this question, but that does not mean the question is meaningless. On the contrary, it takes us to the deepest boundary of science itself. Was the Big Bang the absolute beginning of the universe, or merely the beginning of a phase we are able to observe? This question lies at the heart of one of the most debated areas in modern cosmology. According to some theories, the Big Bang was not an ultimate beginning, but only one stage in a much longer and more complex process. These approaches suggest that something may have existed before the Big Bang. One of these ideas is the cyclic universe model. According to the cyclic universe theory, the universe is not a one-time event. It expands, and after a certain period, this expansion slows down and reverses. At this stage, the universe collapses into itself, a process known as the Big Crunch. However, this collapse is not an absolute end. After the collapse, a new expansion begins, leading to a new Big Bang. In this model, the universe is part of an endless cycle of birth and destruction. The universe we inhabit is only one of these cycles. Time, in this view, is not linear, but circular. A closely related approach is the Big Bounce theory. In the Big Bounce model, the universe did indeed collapse in the past, but this collapse did not result in total annihilation. When the universe reaches a certain critical density, the laws of physics prevent further collapse and cause the universe to expand once again. In this sense, the Big Bang is not the beginning of everything, but the transition from a previous state to a new one. According to this model, the universe existed before the Big Bang, but in a radically different physical condition. The key idea here is not a single beginning, but a sequence of transitions. Another powerful and highly debated idea is the concept of the multiverse. According to multiverse theories, our universe may be only one among countless universes. The laws of physics, fundamental constants, and even the nature of time itself could differ from one universe to another. In this scenario, the Big Bang is not the birth of all reality, but the birth of our particular universe. Other universes may have existed long before ours, or may still be coming into existence. In many models, these universes never interact with one another, making them impossible to observe directly. Nevertheless, this idea is seriously considered because it may help explain why our universe appears to be so finely tuned. At this point, the question becomes even deeper. If there are countless universes, why does ours have the properties it does? The multiverse framework offers a statistical answer. We exist in in this universe because it is one of the rare environments where conditions allow life to emerge. In many other universes, such conditions may never have arisen. Underlying all of these models is an even more radical idea, the quantum vacuum. In everyday language, what we call nothing is not truly empty in physics. According to quantum theory, empty space is a restless sea of fluctuating energy. Virtual particles constantly appear and disappear. These fluctuations may provide the conditions necessary for a universe to emerge. Some theories suggest that the universe was born as a result of a quantum fluctuation within this vacuum. In this view, the universe did not emerge from absolute nothingness, but from a dynamic quantum state. From this perspective, the Big Bang is not a deliberate beginning or a cosmic explosion. It is the natural outcome of quantum processes. The universe exists because the laws of physics allow it to exist. None of these theories has been definitively proven, yet all of them point to the same conclusion. The question of what existed before the Big Bang is not unscientific. On the contrary, it lies at the forefront of modern physics research. Trying to understand the beginning of the universe is not only an attempt to understand the past, but also an attempt to understand the nature of reality itself. And perhaps the most striking conclusion is this: the universe may be far older, far larger, and far more complex than we imagine. When it comes to the origin of the universe, scientists do not converge on a single view. The reason is that this subject lies not only at the edge of observation, but also at the limits of theory. The question of what existed before the Big Bang has led even the brightest minds of modern physics in different directions. One of those figures is Stephen Hawking. According to Hawking, time loses its meaning before the Big Bang. In his view, asking what came before the beginning of the universe is a physically incorrect question. Hawking treats time as a dimension of space and compares the beginning of the universe to the poles on the surface of the Earth. There is no point north of the North Pole. In the same way, Hawking argues that there is no time before the Big Bang. In this perspective, the universe has a beginning, but the beginning has no before. Time does not stop there. It never begins there. In contrast, Roger Penrose approaches the idea of a single absolute beginning with greater caution. In the model developed by Penrose, known as cyclic cosmology, the universe consists of successive phases. This framework is called conformal cyclic cosmology. According to Penrose, when the universe reaches an extreme state of expansion, the distinction between matter and energy becomes meaningless. Under these conditions, the end state of one universe can mathematically resemble the beginning of another. In this view, the end of one universe may be the beginning of the next. The Big Bang is therefore interpreted not as an absolute beginning, but as a transition point. Among modern cosmologists, there are significant disagreements. Some physicists argue that the Big Bang represents a true beginning, and that questions about what came before it are scientifically meaningless. Others suggest that the universe is part of a deeper structure, and that the Big Bang marks only the boundary of the observable universe. Researchers working on quantum gravity propose that space and time may not be fundamental, but emergent concepts. In that case, ideas like before and after apply only within certain phases of the universe. This is the core reason why scientific debates continue. Our observations take us as far as the Planck wall. Beyond this point, theory takes over. But these theories are not yet at a stage where they can be experimentally tested. Different mathematical models can explain the same observations, leading scientists to different conclusions. This is not a weakness, it is the nature of science. Science advances not by providing absolute answers, but by eliminating incorrect ones. When it comes to extreme questions, such as the origin of the universe, uncertainty is unavoidable. Yet this uncertainty does not mark where science fails, but where it is most alive. Today, physicists do not agree on the beginning of the universe, but they all agree on one thing. This question is one of the most fundamental questions we can ask in order to understand the universe, because the answer will shape not only where we came from, but the nature of the reality we inhabit. All the theories we have discussed about the origin of the universe point to one clear fact. We do not yet know everything. The question of what existed before the Big Bang does not have a definitive answer today. However, this does not mean that science has reached a dead end. On the contrary, it shows that we are standing at one of the most exciting frontiers of scientific discovery. Throughout the history of science, many questions once thought to be unanswerable were eventually explained. The nature of stars, the structure of galaxies, and the expansion of the universe were once only hypotheses. Today they can be measured, observed, and tested. The same transformation may occur for questions about the beginning of the universe. One of the most promising developments lies in next-generation telescopes and experiments. Advanced observatories, such as the James Webb Space Telescope, allow us to study earlier periods of the universe than ever before. Each new piece of data about the first galaxies, the first stars, and the earliest cosmic structures brings us closer to the moment of the Big Bang. These observations give scientists the opportunity to test existing theories and eliminate those that do not match reality. At the same time, experiments in particle physics and cosmology are offering new clues about the fundamental laws of the universe. Research into quantum gravity, dark energy, and the nature of space-time may one day turn ideas that exist only in mathematical form into physical reality. Perhaps most importantly, the scientific perspective itself continues to evolve. The questions we ask today, using concepts like before, may be framed very differently in the future. Whether time is truly fundamental, or whether the universe is singular or part of a larger multiverse, may be redefined by new theories. This could shift the question of what came before the Big Bang into an entirely new conceptual framework. Perhaps one day we will arrive at a clear answer, or perhaps the answer will be so different that it cannot be expressed using today's concepts. But one thing is certain, pursuing this question expands not only our understanding of the universe, but the boundaries of human knowledge itself. As long as science continues to move toward the unknown, the secret of the cosmos will gradually come into focus. And perhaps what truly matters is not the answer itself, but our ability to keep asking the question. When we look at the universe, we realize that what we do not know far outweighs what we do. The question of what existed before the Big Bang remains unanswered today, but what has always driven humanity forward was never only what we knew. True progress began when we confronted what we did not know. Throughout history, every great leap started with uncertainty. We did not know what the sky was, so we wondered. We did not know whether Earth was at the center, so we questioned. We did not know whether the universe was static or evolving, so we investigated. And each time, encountering the unknown did not stop us. It gave us direction. Today, as we look toward the beginning of the universe, we find ourselves at the same point. Once again, We do not fully understand where time begins, whether there was anything before it, or even whether these questions are truly meaningful. But this uncertainty is not a weakness. It is the space in which science moves. What we do not know challenges our imagination. It pushes us to build more powerful telescopes and to ask deeper questions. As we try to understand the universe, we are also expanding the boundaries of our own thinking. Perhaps one day we will understand what came before the Big Bang, or perhaps the answer will lie far beyond the concepts we use today. But one thing is certain, humanity has progressed, not by avoiding the unknown, but by moving toward it. And now, we leave you with one final question. If the universe has a beginning, where does the consciousness that questions this beginning come from?